Good day, everyone. We're reviewing Wetzel's Limnology textbook, and more specifically, today we're looking at motion induced by changes and differences in densities. And we'll be picking it up right here. This is chapter 8 and in water movements. And why don't we get started? The flow of cool water out of shallow regions as downslope currents and its replacement by warmer water has been called a thermal siphon. Recent observational and modeling studies indicate that the flushing of the shallow regions can occur from approximately midsummer onward toward winter as lakes begin to cool in temperate and subtropical regions, as was evident in polymictic Lake E6. Recent modeling illustrates how wind and heat loss combine to moderate the flows. Horizontal flows also occur if there is more wind-induced mixing offshore such that the water there is cooler. In that case, warmer water from inshore will flow offshore. These flows can occur within small lakes and large ones and can contribute to the development of stratification in offshore waters. Such flows are attributed to the restratification of 5,600 kilometers square of Lake Albert in East Africa and the northern waters of 85,000 kilometers square of Lake Victoria, on the cessation of the southeast monsoon, resulting in greater cooling to the south in this East African Great Lake. Horizontal convection can be a continuous process in ice-covered lakes as flow moves toward the deeper location and upward flow occurs to balance it, and at times not only one but two circulating layers may develop. When one lateral boundary of a lake is warmer or cooler than the other, horizontal convective circulation can also develop, such that has been modeled for Lake Tanganyika in East Africa, given the much greater heating of this lake to the north and the considerable cooling to the south, and is hypothesized based on field observation in permanently ice-covered Lake Bonny in the dry valleys of Antarctica. There, due to the cold glacial sidewalls of the lake and also taking into account the salinity of the lake, which contribute to its density, a near continuous flow is expected with warmer water rising on one side and cooler water descending on the other, with horizontal flows resulting from continuity. The observational data includes evidence for the expected intrusions. Double diffusive convection motions that results from the different diffusivities of heat and solutes occurs in lakes in which both temperature and salinity contribute to density. When the stratification consists of cold, fresher water over warmer, somewhat saltier water, salt fingering may result and lead to a characteristic staircase structure in a temperature profile. When the stratification is reversed, with warm salty water over cooler fresh water, double diffusion results, and convective motions result again. Conditions that enable these two types of motion are reviewed in short. The staircase temperature profile that can result from double diffusive convection in a lake were first noted in a 540 meters deep meromictic Lake Kivu. Subsequent efforts quantify the increased fluxes of heat and solutes resulting from this process. The stepped temperature profiles have also been noted in Lake Vanda and Lake Myers in the dry valleys of Antarctica. Convective flows provide a mechanism whereby solutes, dissolved gases, or particulates produced at boundaries can flow offshore. Laboratory studies have provided equations that allow the calculation of expected flow velocities and flushing of nearshore regions. The velocities U of the flows can be computed as a steady state as U approximately G alpha delta of T and H, where G is gravity, alpha is the thermal coefficient of expansion, delta T is the temperature difference between inshore and offshore water, and H is the thickness of the intrusion, and all of this to the power and half, which is, in this case, the square root. Tracer studies have identified the offshore flows of solutes from differential heating and cooling. Due to rapidity of the flows from horizontal convection, it may be difficult to discern whether increased solutes at depth in the water column are produced locally or result from the convective motions. The use of 3D hydrodynamic models with tracers embedded illustrates, for example, when increases in dissolved gases such as CO2 result from respiration in nearshore regions as opposed to respiration in offshore sediments. Convective motions in ice-covered lakes, horizontal convective motion, also occur under the ice and drive circulation when the action of wind is limited. In that case, since the temperature of maximum density of fresh water is 4 degrees centigrade, sediments heating the overlying water can increase density and cause a gravity current that then flows downslope. These flows may be enhanced by further increases in density resulting from mineralization in littoral sediments and freeze out and any settling of solutes during ice formation above shallow waters. The result is the well-known inverse temperature stratification found in ice-covered lakes. The product of respiration also accumulates in the deeper locations, and anoxia tends to develop. Tracer studies illustrated the horizontal convective circulation in ice-covered lakes. In springtime, heating below the ice when temperatures are below 4 degrees centigrade leads to penetrative convection. Greater heating of inshore water at temperatures below 4 degrees C increases the density such that offshore flow results causing heating offshore, another example of the thermal siphon described above. Considerable effort has also been conducted to quantify the convective flows under the ice. Such efforts include the methodology to calculate the velocity of gravity currents, the velocity and pathway of the full convective circulation, and the velocity and nature of the plumes from penetrative convection. The velocity of the gravity currents is of the order of millimeters per second, and the resultant upward flows are much lower, such that it could take months for a parcel of water starting at the lake bottom to reach the surface. Downwelling plumes from penetrative convection also have velocities of millimeters per second. Penetrative and horizontal convection have been modeled, and Raman have quantified the influence of rotation on the extent of horizontal convection. Modeling has shown that the combination of the rapid decrease in temperature immediately below the ice combined with the cryo concentration of solutes can create the temperature and salinity stratification conducive to double diffusion in the near surface boundary layer. The extent of mixing deeper in the water column is expected to depend on the strength of the respective temperature and salinity gradients. So before we move on, let's look at figure 8-33. So we have convective circulation and stratification in lakes under the ice. So at temperatures below 4 degrees C, sediment heating of the overlying water creates density currents that flow downslope. Respiration of the sediment-water interface produces solutes that contribute to the increased density and the near bottom flow. Upward flows result in an overturning circulation. B, temperatures and solutes stratified as warmer solute-enriched water flows to the deepest point of the lakes. And C, later intrusion flow at progressively shallower depths due to the increased density and the lower water column. With reduced near bottom flow, anoxia develop and methane may accumulate. So this is pretty much like a cycle of a lake that has where you have a density difference based on temperature, but also based on solutes. And so it goes through the cycle of it. So first we have horizontal convective circulation. So at temperature below 4 degrees C, sediment heating of the overlying water creates density currents. So you have an ice layer here that flow downslope, respiration of the sediments, and water interface produce solutes that contribute to increased density. And so we have increasing in density here, upward flow, okay. Then B, we have temperature and solute stratify. So we have stratification. As warmer solute-enriched water flows in the deepest point, so we have warmer water here. And then later intrusions flow at progressively shallower depth. So then now we have intrusion coming in, and it's overcoming this stratification. due to the increased density in the lower water column. So we have increased density here with reduced near bottom flow. So we don't have as much of a bottom flow like we did here. And we may have anoxia develop, and that may produce methane. Okay. The extent of mixing deeper in the water column is expected to depend on the strength of the respective temperature and thermal gradient, and salinity gradient. Thermal bar. An additional convective circulation is set in motion as a result of density gradients arising when shallow near-shore waters heat more rapidly than the open water mass following ice-off. In Lake Ontario, for example, inshore shallow waters stratify while offshore water temperatures are below 4 degrees centigrade and may be universally stratified. The narrow transition zone between inshore and offshore waters is called a thermal bar. It consists of a nearly vertical 4 degrees centigrade isotherm. Water flowing from inshore and offshore location converges at the thermal bar and flows downward. The density-driven circulation is dependent on the bottom topography, with a more pronounced circulation and considerable descending motion inside the thermal bar zone of convergence in lakes with steep slopes. The downward density-mediated currents outside the thermal bar can penetrate to deep strata or bottom layers and cause appreciable convective mixing, for example, Lake Baikal. The Earth rotation combines with the density gradient to induce a counterclockwise coastal current inside the bar. So 834, formation and progression of a thermal bar in Lake Ontario through early summer, and loss of the thermal bar with the progression of the summer. Figures to the left, surface view with the 4 degrees C isotherm in red, and figures to the right, cross-section with arrows indicating the direction of water flows. 4 degrees C is shaded red. Note the vertical orientation of isotherm indicating the thermal bar. So let's see here. Surface temperature, mid-lake surface temperature. So we have a thermal bar right here. And then we have erosion of that thermal bar, and with the usual stratification going on right here. So here we're not dealing with time because we've been kind of used to looking at isotherm and with the time being on the x-axis. Here we are looking at a transect of the lake, mid-lake, north-south temperature. So probably right here, something to that effect, assuming north is up. And so this is water flow. This is the 4 degree isotherm, or isotherm. Okay. The thermal bar moves progressively further from shore as the heat influx continues to warm the larger open water mass. Little mixing occurs between inshore and offshore waters, and in some locations, a significant portion of inshore water may originate from runoff. Finally, thermal differences between the inshore and offshore regions are reduced to the point where stratification of the whole basin occurs. Thermal bars commonly occur to some extent in lakes with a period of ice cover. In small lakes, the phenomenon is transitory, often lasting only a few days. In large lakes, however, the transition to stratification of the whole basin may take weeks, as seen in the example from Lake Ontario. As a result of the thermal bar, inshore waters are isolated and can warm more rapidly than those offshore. With the warmer temperatures and potential increased nutrient supply from surface runoff and river discharge, productivity can increase earlier in the spring in the nearshore waters compared to the open waters. Pathways of stream or river inflows. The pathway of a stream or river as it flows into a lake or reservoir depends on its density and discharge, with the initial density of the incoming water determined by its temperature, solutes, and the quantity of suspended material. At the river mouth, streams and rivers displace and mix with the lake water, and density differences between the inflow and the surface lake water cause pressure gradients. Thus, the density of the inflow changes depending on its momentum. As the incoming water continues to flow into a lake, mixing may continue further, changing its density. If the density of the incoming water, rho 0, remains less than that of the ambient lake water, as is the case when stream or river water is warmer than lake water in summer, the inflow will travel over the lake water such that the incoming water is an overflow. Otherwise, as for cold and therefore denser inflows entering a warmer lake, the incoming water will plunge and then travel along the lake bottom for some distance. All right. So 835, cross-section of a lake showing entry of an inflow from a stream. So we have a stream, we have an entry. This is warmer water coming in from the stream. And as they were saying, this is the tongue of warmer water because it's not as dense as this, as the colder water will stay on top. And then let's see, so we have B, interflow, where the density of the incoming water after initially mixing with lake water is intermediate. So there's mixing between the water from the stream and water from the lake, and so therefore the temperature is intermediate between the warm water or warmer water and the colder water here. That is lake-based water, I believe. Well, probably a little bit. There's probably a contribution to the stream as well. Let's see, and then pink warm, yeah, right, and then blue cold, and then gray is intermediate, and then underflow blue cold when incoming water is denser. So here we have denser water that is colder than the lake water, and it's sinking and it's moving, therefore, at the bottom of the lake. The resultant shear contributes to further mixing between the plume and the lake water and a further modification of its density, typically decreasing the difference between it and the ambient lake water. The plume will either flow offshore into the lake at a depth equivalent of its new density as an interflow, or if its density remains greater than that of the lake water, it will flow along the bottom as an underflow. In fact, incoming inflows often split such that they intrude at multiple depths. Whether they do so depends in part on the momentum of the plume relative to any density differences within it, on the stratification within the lake, and on the suspended sediment load. Detailed analysis of these mixing characteristics and the dimensional indices used to predict the behavior of the plume are given by these authors. Discharge varies widely seasonally, not only in volume but in the accompanying load of dissolved and suspended materials. For example, in alpine situation, the density of river water is typically greater, cold, high dissolved and high and particulate load, than the recipient water, and underflow is common, particularly if glacial erosion at the head of the river contributes to the suspended load. During the summer, although alpine river water, inflow water is still cold, its sediment load and therefore density can be reduced by dilution with runoff from snow and ice melt. In the summer, then, alpine rivers may flow into the Metalimnion. This situation has been documented frequently. A particularly striking case is seen in Lake Constance, where light penetration is abruptly attenuated in the Metalimnion over large areas of the lake by the intrusion of river water with a high suspended sediment load. The pathway and extent of mixing of inflows with ambient lake water can modify nutrient cycling and biological productivity. The extent of mixing with lake water depends in part on discharge rates. At high discharge rates relative to lake volumes, overflows and interflows may mix and displace a considerable portion of the ambient lake water. When discharge is lower, inflows may mix more slowly with lake water. For example, incoming storm water first mix near the inlet and then intruding into the top of the Metalimnion and base of the upper mixed layer into the lake, where it was subsequently mixed by processes such as penetrative convection. In other years, inflows into the Metalimnion were not mixed into the Epilimnion for several weeks. Similar pathways have been noted in warm water reservoirs with thickened Metalimnia. In regions with persistent inflows, whether stratification is due to solar radiation or on the inflow of weather, stratification breaks down due to wind mixing, can be predicted from dimensionless indices similar to the comparison inherent in the Monin-Ubukov length scales. These indices include buoyancy flux from heating and from the inflow and wind shear. In large lakes, the pathway of incoming water is modified by the Coriolis force. The extent that incoming snowmelt flows into lakes under the ice and mixes can be important for their light climate, their nutrient supply, and the fate of climate-forcing trace gases. Early experiments indicated that while lakes were still covered, much of the incoming snowmelt was an overflow and flowed out of the lakes before mixing. In 1.5 kilometer square Toolik Lake, the incoming water is initially an overflow due to its cold temperature. Even as the stream water warmed, it continued to flow near the surface under the ice as it was more dilute than lake water. The extent to which the incoming water mixed downward depended on the timescale of advection relative to vertical mixing from penetrative convection. Based on a mass balance, only 10 to 15% of the dissolved organic carbon was retained within the lake. In smaller Arctic lakes, incoming snowmelt tends to flow through the lakes. However, when discharges increases rapidly, it can displace water in shallow embayment, such as denser near bottom water in this location flows offshore as a gravity current. In small lakes in the Sierra Nevada, discharge is sufficiently large that it displaces appreciable volumes of lake water, including solutes released by sediments over the winter, and supplies terrestrial organic matter that fuels subsequent microbial activity. Incoming glacier melt water can carry large concentration of suspended material whose influence on lake ecology depends upon its depth of insertion. When these cold inflows occur after lakes have warmed and stratified, much of the plume flows deeper in the water column. Some of the suspended load enters the upper mix layer as the water initially mixes with lake water before plunging, and some may be upwelled and mixed into the upper water column by strong wind events. When settling rates of particulates are rapid enough relative to rates of horizontal dispersion along the main axis of the lake, downwelling irradiance may be sufficient for photosynthesis downstream of the incoming plume. So I think that will be it for today, and we'll pick it up tomorrow with subsection E, combined processes, mixing, and ecological implications. Thank you, and have a great day. Bye.